Good afternoon, everyone. I'd like to introduce myself. My name's Dermot Monaghan from the company Gencoa, and I'd like to acknowledge my colleagues Victor Bellido and Robert Brown for the support they've given the company and myself over the last 25 years. Today I'm going to talk about the full range of magnetic array options for planar magnetrons, and there's a lot of choice, not too much, but you can make your own mind up on that one as we progress through. So just to introduce Gencoa, we've been in business for 26 years, I'm glad to say, and we're operating in the field of component manufacture for the thin film and plasma field. So we're involved in producing magnetrons, plasma sources, controllers, various types of devices used for vacuum thin film coating. We're heavily involved in process development, so we run a range of testing systems in Gencoa. We have 10 different vacuum arrangements systems which we can run tests, and we generate coating structures so we can test as we develop the sources, what kind of structure that we're producing. So in terms of magnetic design for planar magnetrons, there's a lot of flexibility, but there's also a lot of need to and a lot of detail to be looked into if you want to optimize the various aspects involved in sputtering. So this is just a list, not comprehensive, but these sorts of considerations need to be taken into account when you're choosing or producing a magnetic field. So target cleanliness is one element, so that means the target is in a state which is clean, and that reduces defects. So if there's got redeposit on a target, that can produce arcing, which then or dust, which then can find its way into the coating. Pair of operation, so DC, medium frequency, RF, high PIMs, all actually have different requirements magnetically. Pressure of operation, so some processes you want to run at low pressures, you need very strong fields. Equally, if you're running at high pressures, you need weaker fields for various reasons. Voltage of operation, similar. Strong and weak fields help that. So if we want a low voltage operation for, say, sputtering TCO materials such as ITO, then again we need to tend to go towards the high strength field. Layer uniformity is related to also can be fed back to the distribution of the magnetic field on a magnetron, and also that the erosion is uniform and the target length is appropriate, etc. Energy required for the growing film. Magnetrons can be used to add energy, so they can add extra energy for decorative and hard coating processes, and I'll show you the way that is done by unbalancing sources. And then also interaction with magnetic field lines with anode substrates and other vacuum components, very important to complete a system design. Sometimes the substrates are not very tolerant to heat, so you have to be careful that they don't get plasma release from the magnetrons to enhance the heating of the substrate. And then we have practical limitations such as for ferromagnetic materials that need to be sputtered, such as nickel and iron. The magnetic field from the magnetron gets absorbed in the target, so the projecting of the field through the target becomes more difficult. And then obviously very important is budget, so we have various sophisticated magnetic designs, but they're not always appropriate and not always needed for certain situations. So a universal approach is basically taken in creating any new magnetic system, and that's basically modeling. So the modeling is done in 2D and 3D, typically to create a magnetic design which you measure and analyze and think might do the right job. Then you test, so plasma testing is required always to verify models, and then refine. So based on testing results we can go back and remodel, and by doing this cycle you can then get an optimum solution based on whatever situation and magnetic system you're working with. So this is just a list. I'll not go through in detail because each one of these is basically a different magnetic system, and I'm going to send a slide or two on each one to give you the introduction and the basic reason for using the different types of arrangements. Effectively they're bracketed into static, with different degrees of complexity, and then moving systems, so where we introduce some magnet movement to change the properties of the field. So the workhorse of the industry is a two-pole system, so basically a closed magnetic trap, north and south, and we call them sputter wall for balanced, SW, and PP, plasma plume, which are unbalanced designs. So balanced designs are designed to create a magnetic trap over the target, which produces the sputtering, but also limit the amount of plasma which escapes from that region. Unbalanced designs magnetically have an ability to release the plasma to a system, to a process, so it does the sputtering job, but also it allows plasma to be released, and that release of plasma helps the energy in the system and can produce, let's say, denser, more decorative films. So two-pole systems very efficient at sputtering targets. Target utilization is limited up to about 30% because it's a fairly simple field. But it can produce a very efficient sputtering plasma. You can produce quite clean targets if it's designed correctly, and you can mix strengths and degrees of balance and unbalance. So it's fairly flexible and efficient, and also it's the lowest cost option for the choice. High yield design, HY, is our biggest selling product, and it's basically a more complicated system. It's a multi-pole design, 7 or 8 lines of magnets depending on the target width, and that creates a flatter field. So a simple two-pole design has loops between 2 poles, and then the high yield multi-pole design can produce a flatter field, and this produces a better distribution of plasma and also a flatter target, higher target use. There's lots of detail, but this is just something to highlight with the high yield, the difference between the balanced two-pole and the high yield design. Sometimes is also in the process detail. So this is an example from Nano4Energy in Spain, who we collaborate with, and it's working with high PIMS plasma, certain mode of high PIMS. Same process, same materials being deposited, same powers, etc. So a standard two-pole system, due to the nature of the field, in the reactive situations with this high PIMS power, can produce quite a large amount of redeposit, whereas a high yield design of the same target has a flatter erosion and has a wider plasma, and it produces a much smaller redeposit area. So what they find is that over a very long period of time, 15 hours in this case, to create a 12 micron thick hard coating on tools, the high yield has a bigger benefit in that there's much fewer defects, much more stable process for the high PIMS. As the process goes on with the standard and the poison target, start to get instability and arcing, and that creates defects in the coating. So basically the message is that the high PIMS does do these processes much better, and this is an example of a hard 40 gigapascal coating on a micro tool for titanium machining. Metallizer magnetrons are used for machinable materials, so it combines the magnetic geometry with the target geometry. So if a target can be machined, then you can marry up the two aspects to produce a much thicker target and also much higher uptime. So we can double the target life using this method, produce much thicker targets, and we can also do things such as encourage high target use and also prevent coating of the anode, so we hide the anode away behind the edge of the target. So a metallizer design is very useful for rapid, high power putting metals on surfaces, and those metals, because they're machinable, you can use this method. Loop sources are a solution to the sputtering of ferromagnetic materials. We do sputter ferromagnetic targets with two poles, high strength versions, and that works, but the target use and the thickness of target is very limited. So we have a number of loop designs which basically projects the magnetic field over the target surface, and it does that by using the magnetic material itself as part of the target. So we project the field through to this pole, these inner and outer and inner poles, and then we can create the magnetron trap over there, and we can sputter thicker targets, and we can get better target utilization. So it's a very nice method of making sputtering of ferromagnetic materials more efficient. Moving on to a dynamic motion source. So this is basically what we call the extra high EH magnetron, XH, sorry. And it moves the magnetic array side to side at varying speeds. So we have a magnetic trap, which is essentially looping over the target. And then we use a motor to drive left and right. And we can vary the speed as well as obviously design the magnetic profile to suit. And the essential result is that we can sputter through the middle of the target and we can create a much flatter erosion. So again, it produces higher target utilizations, 65% for a monoblock and up to 75% for a bonded target. And also it produces a clean target. So it can make longer deposition runs between target change and also reduce material costs. Another moving magnetron is the original VTEC, so variable magnetron. And this has been produced for many, many years, and it's basically a method of moving the in and outer poles independently. So by doing that, we can change both strength and also balance and unbalance. So this is an example just of a magnetic pole. So this shows the outer magnetic poles pushed forward, the central one retracted, and that's creating an unbalanced effect. So the release point is close to the target, and we produce a plasma moving away. In its middle position where both poles are pushed forward, creates a more balanced field. And then in its most extreme balance mode, we're retracting the outer magnets, pushing the center magnet forward, so strengthening that. And we're changing the release point, moving it further away. So in this case, we have lower release, more balanced arrangement, and less energy going into the process. So this is just an example. These are variable, the VTEC, the original ones. So the manual actuators are used to move the inner and outer poles separately, and we have a readout for that. And this shows in one system between two settings, so that the process, the system operates at 1.7 amps with its in this mode of setting, and then changes it down to 0.7 amps for other parts of the process to create the optimum coating, hardness and stress and adhesion levels. So more recently, we've introduced what we call the VTR. So this is a rotational element. So the original VTEC, moving magnets back and forwards, is relatively expensive because we're moving big bulks of magnetic material with strong interactions, etc. The rotation can be added to a source quite simply on the outside vacuum, and basically it can be done manually or motor driven, and it does a similar job in balancing and unbalancing that the VTEC does. It can't create the strength to the same degree, strength variations to the same degree as the original VTEC, but it does the balance and unbalance in a faster and also more cost-effective way. Plus can be motorized quite simply by two motors which are turning the poles. So this just shows magnetic design, magnetic field. If for a certain source, no VTR fitted, it's just got the magnetic poles in the body. This is when we fit the VTR and we've got it in its most balanced, so we can see we've got a very strong interaction and balance field with the anode, so minimal release to the process, and we can direct electrons away, which is useful for certain processes such as hard carbon. And then the VTR in its most unbalanced form, where we're releasing the plasma to the process and producing the ion energy that we need to assist. So just an example of the VTR on an industrial machine made by PVT, Plasma Vacuum Technique in Germany, and it's just comparing the ion currents at the substrate in the most unbalanced mode and then the most balanced mode. So actually here we can see 32 amps of ion current is generated on the substrate. This is with high PIMS power in the unbalanced mode, and then just 10 amps with the balanced mode. So for the same power effort, you can create different enhancements in energy at the process just by changing the magnetic properties. So the VTFlex is a variable magnetron which moves individual poles down both sides of the magnetrons to either tilt or retract, and this creates a means to change the magnetic profile at will down the target length. So we can go from a flat uniform low strength field to a high strength field. We can tilt it from one side to the other, so gradually increase the strength or reduce the strength down the target, or we can do the concave or convex strength fields. So this can be used to tune and get much higher uniformity, and also it can be used to counteract RF plasma problems, large area RF plasma problems that tend to be more non-uniform. We can use a magnetic adjustment to counteract that. The VTS is again a simple retraction and forward and back movement of the magnetic array. So this is used to create field strength variations. So if the array is fully forward in this source, we're getting 650 Gauss over the target. As it's retracted 15 millimeters, it goes down to 300 Gauss. So that can be used simply just to retract the array as the target erodes and keep the voltage constant during the process, and which also improves target utilization to some degree. And also it can be used to switch between, say, PVD and CVD type processes. So where we in sputtering mode, you have a high strength on the target, and then in the CVD mode, you're going for a low strength on the target. And again, a motor is just connected to change the position, and then there's also this just an encoder to show the position of the magnetic array. High uniformity magnets or magnetrons are basically where we have more time and more effort tuning the magnetic array. So typically, a magnetic array is once built and put into a body, we always scan the magnetic array, and typically we're keeping close control of the tolerance of the parts and the magnets. You can achieve a field between 2 and 3% variation over the length of the target. High uniformity magnetic arrays, we pre-select and check the energy product of each magnet before we use it. Then we batch the magnets and use certain magnets for certain arrays. So we can basically get a much tighter variation in magnetic field down the target length, and that corresponds to a tighter uniformity, which can be important for some applications. And also you can minimize machine-to-machine variation by always characterizing the total energy of the magnetic array. So just trying to summarize, this is we've got rectangular magnetrons which can have a wide range of magnetic options depending upon the application. I just introduced some of them, and depending on your process and your needs, you can choose one or the other or a combination in the same system. So flexibility is available. This is just a summary of some of the plasma pictures we've taken. I've taken them out of the archive, historic pictures, and these are from the first 15 years of operation of the company. So planar magnetron has been in the market since the 70s, even 60s, but there's still developments and advances happening in the field all the time. And again, the final slide. Thank you very much for your attention. Planar magnetrons, very flexible, come in all shapes and sizes. And if you have any questions, I'll be available online in the virtual chat. Thank you very much.